Okay, good morning. Let's settle down. A quick announcement, or rather not an announcement as much as advice. I noticed that many of you are still not on Piazza, so I suggest that if you are not checking Piazza, that you should do it regularly, because you will miss announcements, things of importance to the lecture and the class, and that's our main way to communicate with you about generic things. So if you don't check Piazza, then you will miss things that are important, okay? So as soon as you can, please sign up for Piazza. Okay, all right. So we're going to discuss two main topics and maybe try to start a third topic if time permits. Let's start with languages and the importance of languages. We already seen strings last time, right? So what are strings? Strings over a finite alphabet are just sequences, finite sequences of letters from an alphabet. What is a language? A language is simply a subset of strings. Okay, and why do we use language as opposed to a set of strings? It's just in the context of historical context, a language is it's just a notation from historical context. There is no reason to give it a name like this, but that's what happened. Okay, and because languages are just sets, you can do things like intersection, union of sets, and difference as the usual set operations, right? So it's not any different. The union is the set union, intersection is the set intersection, the difference is set difference, the usual set operations. We say the complement of a language is simply the sigma star minus the difference between sigma star and the language. So the complement includes all strings in sigma star which are not in the language, right? That makes sense? Yeah, okay, that's the standard thing. And we did it briefly last time, but we can also define what is the meaning of exponentiation for a language. It's repeated concatenation, right? So what is L to the n? It is L concatenated with itself n times. Okay. So inductively, what is L to the n? It is for n equal to 0, it is a set containing just epsilon. Okay, that is just a definition. And what is L to the n? It is L concatenated with L to the n minus 1. Okay, so inductively, what it is saying is, this formalism. It's just that L to the n is L concatenated with with itself n times. What is the concatenation of two sets of strings? Do you remember that? What is, if A is a set of strings and B is a set of strings, what is A concatenated with B? Let's recall that definition. Yeah, you remember what a set? You take every string in A, every string in B, and concatenate them, and that's in A concatenated with B, right? So another way of thinking about L to the n is take n strings, any n strings, right, and concatenate them, and take all such strings, and that is L to the n, right? Yeah. And what is L star? Just like sigma star, L star is formally defined as the union of all n greater than or equal to 0 of L to the n. So that all possible concatenation, finite length concatenations of strings from L, right? Make sense? Okay. And L plus is simply all. I mean, we don't include epsilon in that. That's all. Okay. That's the only difference. Okay. Sounds good. So let's just make sure we understand this, right? Okay, let's, what about number 1? Is epsilon equal to the set containing epsilon? Doesn't make sense. Okay. Is empty set the same as the set containing epsilon? No, right? Yeah. Empty set doesn't contain anything, right? Well, the set containing epsilon has the string which is epsilon. Okay, very careful. Epsilon is the reason I'm doing this is to make sure that epsilon is actually some element. It's not nothing. Okay, it's an empty string. Okay, so this set, the second set has one element in it, right? Well, empty set has no elements. Okay, what is empty set concatenated with a set A? Sorry? Is it set A? Yeah. What are two choices? Empty set, A, epsilon, right? Or three choices. So it's a, what is the definition, right? What is the definition of empty set concatenated with A? What should be in it? It should contain, I mean, all the things in empty set concatenated with A are of the form something in A concatenated with something with the empty set concatenated with something in A, right? But what is in the empty set? Nothing, right? So there is nothing in empty set concatenated with A, right? So it's an empty set, not A. Okay. Okay, but what about the same thing? A concatenated with empty set is also empty set, right? Okay, but what about the next one? What is the set containing epsilon concatenated with A? That is A, right? Why? Because, you know, how do you get a string in this set? You take some string in the first set, which is, there's only one string in the first set, right? So it's epsilon concatenated with some string in A. What is that? It's the same string, right? So everything in A is in that set, and nothing but a string in A is in that set, right? Okay, so that makes sense. Just, you know, just to get some comfort. Then it's the same thing for the other one. Okay, this is an interesting question. If set A has 2 strings and set B has 3 strings, how many strings are there in the set A concatenated with B? 6, say, okay. It's a trick question, so think again. Yeah. Right. Yeah. So, I mean, clearly there cannot be more than 6 elements in A concatenated with B, right? Yeah. That makes sense. But the question is, do we always get 6 elements in A concatenated with B? Yeah. Okay. Let's take an example. Yeah. I mean, I claim not. Can you think of sets A and B such that when you concatenate A with B, you get less than 6? Yeah. Yeah, exactly, right? For example, there could be an empty string in A, right? Let's think of an example where it is not, there is no empty string in A and B, and still you can get this problem. Just yeah. Yeah, right? You know, let's take a set of the following form, right? You know, A is, for example, they can have intersection, right? This is A, and B is A, right? And what else? Sorry? Q, okay, then what happens? Do we get you need a third element? Okay. Okay, I guess, you know, if you don't have epsilon, sorry, AQ, yeah, right? So then what happens, right? You get no, you don't get that, right? You get AQ from this and this, and right, okay. So you get, by concatenating this and this, you get AQ, and you get it again, right? By concatenating this and this, right? So so upper bound is 6, but you don't have to have epsilon to get this phenomenon of strings, right? Okay, that's something to keep in mind. Okay, okay, more problems, right? What is empty set raised to 0? strict question again, right? Okay, okay, but we just defined it, right? By fiat we said for any language L raised to 0 is what? Just the set containing epsilon, right? So it holds also for the empty set, right? Okay, it's okay. Again, so if L equal, so this is epsilon by definition, right? Because we define it that way for every L, right? Okay. If L equal to 2, then what is L to the 4? Again, it's a similar question to that. You cannot tell, right? You would think that it should 2 to the 4, right? But it could have less than that, right? So we cannot tell exactly. It depends on the structure of L and stuff. So it's at most 2 to the 4, but it can have less. So what is empty set star? What is L star? Remember what L star is? L star is L0 union L1, L2, L3, everything, right? So for empty set star, what is it? Yeah, because what is empty set to 0? That we already argued is the set with the epsilon. So epsilon should be there in that. What is empty set to 1? That's just empty set. So empty set to 2, to the raised to the 2 is empty set concatenated with the empty set. But all of them are empty, right? We already saw that. So only reason why we get epsilon in that is because of empty set to the 0 has, by definition, has epsilon in it, right? Okay? Right? So what is the set epsilon raised to a star, the cleanish star of the set epsilon? Just the set containing epsilon, right? Because if you concatenate epsilon as many times as in here, it's how many can you get, right? So all possible concatenations, right, of 2 elements. I mean, so you get, yeah, you get 6. Yeah. So what is epsilon raised to star? Does it make sense? Oh, yes. What is this? It's again a trick question. Yeah. Yeah, it doesn't make sense because we didn't define it for strings. Okay, we define it only for languages, right? Sets. So epsilon is a string. We didn't define it even, so it doesn't make sense. Okay, it's not syntactically make any sense, right? Okay. All right. So I'll let you understand these things. Same thing with this, right? This later on, you can figure that out as an exercise. Okay. So why are we interested in languages? So what is the connection with computation and languages, right? And I want to make that a little bit clear because we deal with languages quite a bit. So most of the time, if you think about what we want to compute, the more natural thing that you would think about computing are functions, right? I mean, if you think about, what is it that we want to compute, the main thing we want to compute, I mean, in terms of the original motivation would be, I want to calculate, right? That is the motivation for computation. Calculation is the first thing we do, right? Give me the product of these numbers, or add these numbers, or right? And so functions are more natural things that people would think of that they would want to compute, right? So anything, almost anything that you want to compute can be cast as computing a function from strings to strings. Why? Because anything you can think of can be written as a string, right? I mean, ultimately everything is basically symbol manipulation. So almost anything, that's kind of maybe a meta point, but strings are so powerful because it's just symbols, and symbols are what we manipulate, right? So functions which take strings to strings are essentially universal. Anything you can think of or can be put in this fashion. So almost any problem you can think of, you can compute as this, right? So okay, functions are what we want to compute, right? Again, they're all the examples you can think of. So a special type of function or restricted type of function is what are called Boolean functions. What are Boolean functions? These are functions where the output is not a string but either just 0 or 1. Okay? So you can think of it as the answer is this function for every string is either yes or no, right? They're clearly simpler functions, right? So the simple problem, is the length of this string odd, right? That's a problem, right? The answer is just yes or no. It's not what is the length of the string, right? But that's a smaller class of functions, but it is essentially as powerful as the general functions. It's not so simple to see that, but this is a very the nice thing about this is that the output is just 0 or 1, right? For every string, the output is okay. So if you can solve these Boolean functions, you can essentially solve any interesting function you want by other tricks. Okay. So now I want to claim that there is a bijection between Boolean functions and languages, and it's a very simple bijection. What does it mean? That every Boolean function can be thought of as a language, as a subset of strings. Why is that? So if I want to think of a Boolean function, what does it mean a Boolean function? What does a Boolean function do? For every string, it either says 0 or 1, right? Okay. So I can associate a language with it, which is the set of all strings for which the function value is 1. Okay. So if I think of a Boolean function, I can associate a language LF, which is the set of all strings such that f of w equal to 1. Okay. It's a simple definition. There is nothing, right? Okay. So the other way is also true, that if I want to think of a language, I give you a language which is simply a subset of the strings. How can I encode it as a function? I say that here is a simple function. For every string in the language, the function assigns 1. For every string not in the language, it assigns 0. Okay. Is that clear? So languages are essentially the same as Boolean functions. Okay. Okay, then this natural correspondence gives rise to the following problem, which is the same as given function f computed is the same as saying given a language L, the language recognition problem is the following, right? What is the language recognition problem for a particular language L? Here is the problem. Given a string W, is it in the language or not? Okay. Okay, so what is a simple problem that your compilers do? You write some code, and what is the compiler doing? First thing it does suppose you write a C program, what does it do? The first thing it does before it translates it into object code or something, it has to check whether the C program is a valid C program, right? Did you write a syntactically valid C program, or did you write some gibberish, right? Okay, so that's a simple language problem, which is also a functional problem, right? Okay, so that's all it is. Language recognition problem is, what is the language we're interested in here? All valid C programs, right? What is valid? Syntactically valid C programs, right? So some strings are valid C programs, some strings are not valid C programs, right? However, you don't quite know what that means, right? Right now, what is a valid C program? We'll come back to it later, but oh, come on. It says not an exit clearly on that. Okay. Please don't use that door to go out, okay? Especially in the middle of the class. Okay, so so that is the simple that's the as general as Boolean function. So language recognition is a very important problem, right? So why do we think of it in two different ways? For some problems, it is more natural to think of it as a function problem. For some problems, it is more natural to think of it as a language recognition problem. For example, the compilation problem makes more sense as a language recognition problem. What is a string? Is it a C program or not, right? For computing the length, it doesn't look like it's a language problem, more like a function problem. Okay, so now let's ask the following thing, right? So we saw the definition of what is an infinite set is. When you say it's countably infinite, what does it mean? That means that there is the number of objects in the set is as much as the number of integers, right? Okay. We saw earlier last lecture that how many strings are there? If for a finite alphabet, how many strings are there? It's countably infinite, right? The same as the number of integers, roughly, right? Because it's a bijection. But now I'm going to ask the following question. How many languages are there? Okay, it's a little different question, right? Okay, what is a language now? The language is a subset of strings, right? Okay, so I'm not asking how many strings are there, how many languages are there? How many languages are there? So every subset of strings is a language, right? So it's the number of subsets of strings, right? So what is it? It is the power set of the set of strings, okay? But how many strings are there? Roughly the number of integers, right? So the number of languages is how much? The power set of then roughly the number of integers. Yeah. Okay. Quick question. Yeah. So the question is how many are there, right? So the natural question that people wanted to understand was, is it countably infinite? Okay. So take a finite set. If I suppose I have a set of 10 elements, and I ask you how many are elements, what is the size of the power set of that? How many subsets of a set of size 10 are there? 2 to the 10, right? Yeah, is that okay? What is the power set of a set of size 10? It is 2 to the 10, right? Because every element could be in a set or not, right? Yeah, no? Yes or no? Okay, that we go back to 173, right? Okay, so for a finite set, the power set is clearly bigger than the size of the set, right? It's big, much bigger because it is 2 to the 10. But then it's a little subtle to ask, okay, if the set is infinite, the power set should be bigger, right? Somehow it seems intuitive, but it's not so obvious, right, how to prove it, because infinity is subtle, right? So Cantor was the one first who figured out that, okay, here is a proof technique. You will quickly see it, that the power set of integers is bigger than the integers. What does it mean it's bigger? How do you formally prove it's bigger? That there is no one-to-one correspondence from the integers to the power set of the integers. Okay, so what does it mean? That the power set of the integers is bigger than the set of integers, right? Okay, so in particular, I mean, in fact, this is true for all one. The number of languages is much bigger than the set of strings. Okay, okay. So how do we prove this? Well, let's just prove it. Recall the 173 proof that the power set of the integers is not countably infinite. Do you remember seeing that? Or let's not worry about, we'll redo the proof, but do you remember discussing this? Yeah? Okay, so this is called the diagonalization argument, right? What is the argument? So suppose for proof of contradiction that indeed the power set of the integers is countably infinite. What does it mean? There's a one-to-one mapping, right, between integers and the power set of the integers, but it's the same as saying that I can take all sets and number them somehow, right? There's a numbering of the sets so that every set will come in the numbering somewhere. That's the same as saying one-to-one bijection between the integers and the power set of the integers. Okay, so we're assuming that it is countably infinite, and we'll get a contradiction, which would imply then that it is not countably infinite. Okay, okay, so we're assuming that it is countably infinite. So there is a sequence, there's a numbering of the sets as S1, S2, up to infinity, so that every set is going to come in the numbering somewhere. Okay, so then what is let's look at this, what's called the diagonal set. What is a diagonal set? It's a set of all numbers I such that I is not in Si. Remember, S1, S2, S3, S4, so on is a numbering that is supposed to exist because it's countably infinite, right? We made the assumption, and then we're going to get a contradiction. By the assumption, there is a numbering, and then we're going to create this diagonal set D such that D is this, by definition, D is I, all the numbers I, such that I is not in, this should be, sorry, Si. Okay? Okay? Is well defined. D is well defined, right? Agreed? Okay. Now D is a set, right? D is a set of numbers. If D is a set of numbers, it must come in this ordering somewhere, right? Yeah? By assumption, D should be in the numbering somewhere. Yeah? Where is it? Well, it should be Sj for some j, right? So far so good? Okay. No, not so good. Okay. Okay. So I am trying to prove that the power set of the integers is not countably infinite, right? How am I going to prove it? By contradiction. How does the proof by contradiction go? You assume that it is countably infinite. Okay. What is the implication of assuming it's countably infinite? That we can number all the sets of numbers as S1, S2, S3, and so on. There is a numbering somehow. Somebody gave that numbering because it is supposed to exist. And every set must be in that numbering somewhere, right? I assume, because we assume that. Okay. Well, and then I'm creating a new set called D based on the numbering as follows. D is a set of all numbers I, so that I is not in Si. Okay. It's a set of numbers. So it's a fixed set, right, based on that numbering. So it must be, every set is in this numbering somewhere, right, by assumption. So where is D? Well, it must be some Sj for some j, right, finite j. That's what it means to have enumerable. Okay, so D is Sj for some j. Now the question is j in D or not, right? Let's ask, is j in D? You should get counted, we'll get a contradiction, right? Is j in D? If j is in D, what happens? Sorry? Yeah, if j is in D, but remember D is Sj for some j, right? But D is a set of, let's look at this, j should not be in D, right? Okay? Okay, we get a contradiction if j is in D, right? Why? Because if j is in D, but because D is equal to Sj, but by the definition of D, j should not be in S, right? So j cannot be in D. Okay? Is that clear? I'm asking the question, is j in D, right? And now you say, oh, okay, let's check. Because D is the same as Sj for, right? What is the definition of D? Is a set of all I such that I is not in Si. From that, if you apply it to j, then j should not be in D. Okay, so j cannot be in D. Now the question is, what if j is not in, so there are only two possibilities for j, right? Either it's in D or it's not in D. Suppose j does not belong to D. Okay. Well, j does not belong to Sj then, right? Okay, but by the definition of D, j should be in D. Okay. So in either case, you'll get a contradiction. And so if you get a contradiction in either case, and since every element should be in, for a fixed set and a fixed element, an element should be either in that set or not in that set, right? And in both cases, we are getting a contradiction. So what must go wrong? Our assumption must have gone wrong. What was our assumption? That the sets can be numbered. Okay? All right? Yeah, there's infinite sets, yes. No, but the assumption is that all the subsets are numbered, right? That's the assumption of having a bijection with integers. Okay. Now the thing is, this is a when Cantor went mad. Okay, he's a great mathematician, right? People couldn't wrap their heads around this argument, right? And it's not an easy argument, right? You just in the sense that it's hard to understand it. Okay, it's hard to understand argument, right? You can go through it. There's nothing wrong with it. It's correct, all that, right? So I'm not going to spend more time on this simply because it will take a long time to sort of get the hang of it, right? So the point I want to make is that I just want to, this is a review from 173, that the set number of languages is way bigger than the number of languages. Okay. So what does it mean for us, right? Let's go. Don't worry about the proof. If you don't get it now, you can think about it later. What does it mean for us? Okay. What it means for us is the following, right? How many C programs are there? Well, each C program is a string, right? Yeah? So the number of C programs is the same as the number of integers. Yeah? Okay. But how many problems or languages are there? Well, we just argued because the number of languages is way bigger than the number of integers. So the number of problems we want to solve is way bigger than the number of programs we have. So what does it mean? it means there are so many problems that we cannot solve because we don't have code for it. Okay? Okay, if the number of problems is way bigger than the number of programs, what does it mean? That means that there are many problems for which there are no programs, right? Just, yeah? Okay, so there are so many, in fact, the number of problems that we cannot solve is way bigger than the number of programs we have. So, immediately, if you believe that C or any programming language is a notion of computation, there are way too many problems we cannot solve. Okay, it's just an elementary fact based on this counting. Okay, okay. So then obviously there are okay. Then the next question is, okay, sure, but maybe they're not interesting to us, right? Maybe there are many hard problems. Why do I care? If all the problems I want to solve are solvable, well, I don't care if there are problems that cannot be solved, right? That's a reasonable, pragmatic answer you can give me, right? Who cares if there are difficult, uninteresting problems? Maybe I never want to solve them anyway, right? But that's not true. In fact, there are many problems that we want to solve, which we can prove also are not solvable, not by this direct argument, but I mean, the same argument will give us more, but I'm not going to do it right now. We'll come back to it when we do Turing machine, okay? Okay. But the reason is that why we went down this path is that once you realize that there are many interesting problems that you cannot solve, then starts the business of, oh, what can you solve? Okay, what are interesting problems that you can solve? How do we understand what can be solved? Okay, so that's really there's an exercise for you about finite languages. I'll skip that now. I want you to argue that the set of all finite languages is also countably infinite. Okay, it takes some time to understand what that is, but you can do it later. Okay, so we are really interested mainly in infinite languages. Okay, so now let's at least roughly we know that there are difficult problems, right, which we cannot solve. Okay, then we're going to go to the other extreme and start with easy class of problems or languages. Okay, and they have both the mathematical interest as well as the fact that they're useful in practice. Okay, so the other extreme is what are called these regular languages, and we'll learn a lot of tricks in understanding regular languages and regular expression. Many of you have heard of regular expressions, I assume. Yeah, people have not heard of regular expressions. Yeah, can you raise your hand? It's okay. It's just a simple thing. Not heard of regular expressions. You probably use it implicitly in searching without realizing it, but we'll see. So, okay, what are regular languages? So these are a subset of languages, okay, and they are defined inductively and mathematically as a class of languages. Okay, we'll see that there are different characterizations. Okay, they're a very simple class of languages. How are they defined? Okay, let's hear as a definition. So we fix an alphabet always, finite alphabet. If I don't say it, assume that there's always some finite alphabet sitting in the background, right? Sigma. Usually it will be 0, 1 or something, but it's okay. Okay, this is an inductive definition, right? Empty set is a regular language, right? Yeah, so empty set should be there in any interesting class of languages, right? Okay. Epsilon, the set containing epsilon is a regular language. Okay. Every letter of the alphabet interpreted as a string is also in the language. Yeah? Agreed? Okay. Now these are base cases, right? These are simple languages, right? Empty set, the set containing epsilon, and the set for every letter, the set containing just that letter as a string, they're all in the regular languages. Okay, now we'll say, how can we build more languages? If L1 is regular and L2 is regular, L1 union L2 is also regular. We're allowed to combine two languages together by union. Okay, not intersection, just union. Okay, agreed? If L1 and L2 are regular languages, you can concatenate them. L1 and L2 is also regular. Okay, yeah. Okay, and the last one is the one which leads to a bit interesting feature, is that you can take the Kleene star, and that's also regular. So if L is a regular language, L star is also regular. What is L star? You can take essentially, arbitrarily long concatenations. Okay, does that make sense? Yeah, that's it. That's the set of regular languages. That's the definition of regular languages, right? Yeah. You may have a small question. Wait a second, maybe everything is a regular language, you know? Yeah. It's not obvious that there is not everything can be a regular language, you know? We'll see that it's actually a very simple class of languages. Not many interesting things are, I mean, in fact, trivial languages are not irregular. But it's not obvious, right, from the definition. Yeah. Yeah. Agreed. This is just a definition of regular languages. Yeah. So what's regular? Let's understand what's regular. Okay. Here is first fact. Okay, so basically what are regular languages? These are by definition, they are closed. What does it mean closed? That if you take an operation and it remains in the set. Okay, so they are closed under the operations of union, concatenation and clean star, right? Because if you take the union of two regular languages, it's back to regular, right, by definition. If you take the concatenation, it's back to regular, right? And clean star, it's good. Okay. Okay, let's understand the very basic thing. I claim that any single string is, as a language containing any single string is regular. Why? Why is this regular? From the definition, why is this regular? So this language I claim is regular. Yeah? No, this is not. There is only one string in it. Not a union. There's only one string in this language, right? How can we make this language from these operations and the base cases? Yeah. Yeah. Yeah, I want to claim that this is the concatenation of this, no? Yeah? Is that okay? Yeah? Any questions on that? I mean, of course you may say, okay, no, to be technical, I have to say like this, I should put parentheses. Yeah? That's okay. Yeah? Yeah? So just like that, any string can be made as a concatenation of the single letters, but because each of those letters itself is a language, we can just concatenate those languages. Because the finite length, we can do it, right? Yeah? Does that make sense? Okay, at least we have that, right? That seems like the minimal thing we need, but that we can get from the basic operation. Okay, every finite language L is regular. What does it mean, finite language? It has only like some fixed, a finite number of elements, right? So what is a finite language? For example, why is this regular? A, B, this three, because it's a finite language because there's only three strings, right? It's not an infinite set. Why is this regular? Yeah? Yeah, well, the single string A is regular, right? This string is regular by this previous lemma, right? This is regular and we can take unions of these things, right? Remember, finite unions are allowed, right? You can take union, right? Okay. So does it make sense? Why this is true? Okay. So here we're using concatenation, here we're using union, right? All right. So this is also fine. Yeah. So far so good. Okay. So we need to understand what these languages are. Okay. So we'll see later on. But why are these interesting? Because they capture some interesting simple things that we can do. So W is a keyword in Python program, right? Why do you think it's regular? It's a finite list, no? So any finite list is regular. So if you have a fixed language and there's a finite list of keywords, that will be regular. For a simple reason, right? Why is this, right? This is also regular, right? Because, well, it is not so obvious, maybe. Yeah, because it's also finite, no? At some level, this is also finite. Well, this is more interesting, no? It's not obvious, right? The set of all Roman numerals is essentially an infinite set, okay? But we can, we can show later on that that's also regular, right? Okay, but this is also more interesting. So the set of all strings which contain CS374 as a substring, okay? That's an infinite set, right? Yeah? Isn't that an infinite set? Yeah, okay. So that's also regular. Why is that? Why is that regular? Sorry? Yeah, so can we see why that is regular? We didn't talk about regular expressions, so okay. I claim that this can be written as sigma star concatenation with what? CS 374 concatenating with what? Sigma star. Okay, do you see that? What are the strings in this? So every string in this will look like some string concatenated with CS 374 concatenated with some string. But that's more or less, that's not more or less, that is the same as this, no? Yeah? So, but this is allowed. Why is this a regular language? Because sigma star is, clearly star is, sigma itself is regular, right? Because it's a finite set. Sigma star, because you're allowed to take the star, that is regular. So the set of all strings is regular, right? And this is regular, this is regular, this is regular, and we can concatenate and we get regular. Okay? So regular languages, even though they look simple, are interesting and useful. Okay? Okay. Now, okay. So how do we keep track of regular languages, right? And this is where we use what are called regular expressions. So regular expressions are a way of making sense of the operations that we are using to define regular languages. Okay? They're just a syntactic notation. Okay? So why are regular expressions useful? Because regular languages are simple and you can express things like, you know, for example, how many of you have heard of this application called grep on Unix? Okay. These days, you know, with tools, you know, when I was an undergrad, we didn't have, you may find it funny, right? We didn't have this Windows and the cursor. I mean, we just had to use this the monitors, just text monitors, right? And in those days, you couldn't have, the tools were very primitive, right? Unix was developed in those days, so you had a lot of command line tools. Okay, grep is a still very powerful command line tool. It's available in all the systems, but it's sitting underneath. If you wanted to check in a file all strings which had CS374, you would use this tool. Okay, and that is a language for so text search and compilers and all that stuff, right? So you needed a compact way to specify that language, right? All strings. So you couldn't write, you know, you can't tell computer, you know, search for this, right? That's hard. I mean, how will the computer understand it, right? So we needed a way to specify it in this fashion, right? In a nice way, and so that's why the regular expressions were they go back to the 50s. Okay, so I'm going to define formally what regular expressions are, and then a regular expression is simply a string itself. Okay, so there's some circularity, but we'll come. Okay, I don't know if you can see it, but this is actually bold case A. Okay, it's a bit hard to see. Maybe I should have used different colors. This is bold case A. So this is bold and this is bold, but it's not very clear. Anyway, this empty sets denotes the language empty set. Okay, this is not the empty set itself. It is a symbol representing the empty set. Okay, you know, some of this may seem like, you know, silly, but we have to deal with logic at some level, right? You know, there is no getting away with it. This epsilon denotes the language containing the language which just contains the empty string. The bold case A, which is not so obvious here, denotes the language just A. Okay, so remember, these are the base languages, right, in regular languages. So we're saying, you know, we need notation to indicate them, and we're just overloading this notation. Okay, so bold A is referring to this language. Okay, bold epsilon is referring to this language. Okay, this is not epsilon. It is a symbol representing the language. Okay, that's how it is. Okay, and then if R1 and R2 are regular expressions denoting the languages capital R1 and capital R2, then we'll use R1 plus R2 to denote their union. Okay, and we'll use R1 R2 to denote the concatenation, and R1 star to denote the language R1 star. Okay. Okay, so here is a correspondence, right? What we are doing, right? See, how did we define regular languages? We said these three are base cases of regular languages, right? Empty set, the set containing epsilon, and for every alphabet letter, the set containing that letter is regular languages. And then if you have regular languages, you can take their union, concatenation, and Kleene star, and they all are regular languages, right? Okay, we are going to set up a correspondence saying, this language, sorry, that should be, that's right. We are going to use as a shortcut A for the language containing A, epsilon for the language containing just the epsilon empty string, and empty set for empty set. And if you had, R1 representing a regular language and R2 representing a regular language, R1 plus R2 represents the union. Okay, and we'll see some examples, right? And so it is just syntactic notation, right? So here are some examples, right? What is 0 plus 1 star? What does it mean? What is it? Language. See, this is a regular expression, right? Okay, but what does this represent? No, so let's go through this slowly. This is representing, right? Yeah. So what is this? 0, 1, right? That is sigma. Star is what? This is a set. This is just sigma star, right? So this is just a set of all strings, right? So this is just a regular expression to denote sigma star. Okay. Okay. So what is this? 0, 0, 1, 1, 0 star, right? Technically I should put parentheses, right? It's very painful to put parentheses. We'll drop the parentheses because we can understand what this means. Okay. Just like arithmetic, we are going to set up some precedence rules. Okay. So let's just go through that, and then we'll see some examples. Okay. For a regular expression R, L of R denotes the language that it denotes, right? Okay. And for example, what is 0 plus 1? What is that language? The set 0, 1, right? Okay. And 1 plus 0 is what? The same set, no? It's 1 and 0. Okay, so you can have different regular expressions to denote the same language. That makes sense, right? We can talk about a language in different ways. Okay. We'll say the two regular expressions are equivalent if their languages are the same. Okay. That the denote are the same, but we'll see why. Okay, now the parentheses are a pain, so we'll get rid of the parentheses because we understand what we're talking about. How do we get rid of the parentheses? Well, just like in arithmetic, right? Plus will have low priority. Concatenation will have high priority because it's like multiplication, and star has the highest priority. It's like exponentiation. Does it make sense? So what does R star S plus T mean? It's actually R star first, concatenated with S, then T. Yeah? We want to get rid of parentheses because it's a pain to deal with them. Any questions on that? Okay, that's fine. Okay. And then also, RST means that, because it's associative, concatenation is associative and union is associative, RST is simply as RS concatenated with T or R concatenated with ST. Yeah? So these are precedence rule. And for convenience, we'll use R plus, just like with L plus, to denote R star. Okay? It's sometimes useful. Okay? Okay. There's some other notation, don't worry. So, okay, so we need to get used to these regular languages, right? The two skills that we need to get used to are, suppose we have a language in mind, say an English description, we would like to write a regular expression for L if possible, right? We haven't yet realized that there are some languages which are not regular, but we would like to do that, right? The other skill is that given a regular expression R, we would like to understand in English what that language L of R is. Okay, so let's do that and then we'll see. Okay, so this we already saw, right? 0 plus 1 star is what? Set of all strings over 0, 1, right? For the rest of the lecture, we'll assume the only the alphabet 0, 1. So simplicity. Okay. What is this? It looks like CS 374 that we saw earlier, right? What does this regular expression denote? Yeah? Yeah? Yeah, everybody agrees with that? Everybody, any question on that? I mean, I'm going to give some time so that everybody absorbs it, right? Because I was told I was speaking too fast. Am I still speaking too fast? Oh yeah, I see. Okay. You got to slow me down, right? You know. Okay. So it is a set of all strings with 0, 0, 1 as a substring, right? I'll be very slow. Okay. All right. What about this? What is 0 star? So it's strings with only zeros, no 1 in that, right? Okay. What about this? First, let's forget about the star. What about inside? What is it? I want to understand what this is. Okay, how many ones are there in that language? 3. Okay. Can all strings with exactly 3 ones be in that language? Okay. No. So okay, we know that every string in this, I mean, I'm omitting the star for now. We know that any string in this has, I want to claim that this is a language of all strings which have exactly 3 ones. Okay. So one direction is easy to see, right? That if a string in this will have exactly 3 ones. But the question is, will every string with exactly 3 ones also be in that language? No? I claim it will, right? Why? So how does a string which have exactly 3 ones look like? Well, it has to have 1 somewhere, 1 somewhere, 1 somewhere, right? And in between, what should be there? Okay, some zeros, some zeros, some zeros, and some zeros, right? That's a string with exactly 3 ones looks like that, right? It could be 0, I mean, this number could be 0 or more, right? 0 or more zeros, right? Okay, but they're all going to be here, right? 0 star has what? It can have epsilon, 1 0, 2 zeros, 3 zeros, any number of zeros here, followed by 1, any number of zeros, followed by 1, any number of zeros, followed by 1, followed by any number of zeros. So, okay, so this is a language, what? Containing all strings with exactly 3 ones in them. Is that okay? Yeah? So when you take the star of that, what do you get? Yeah? That means, you know, what is the 0th power of that? Just epsilon, right? What is the 1th power of that? Just that, right? That's what is the 2nd power of that? 2nd power is concatenation. So I take a string with exactly 3 ones and then take another string with exactly 3 ones. What do I get? 6 ones. Okay, what is the 3rd power? Okay, 9 ones, right? So the star has all of them, right? So strings with 0 number of ones, 3 ones, 6 ones, 9 ones, 12 ones. So what are the strings? So all strings which have number of ones divisible by 3. Okay, that's it. Okay, yeah. No, but it's a powerful way of describing, no? It's a nice, simple, compact way of describing something that we may be interested in, right? Okay? Okay, so we're getting used to it. Okay, what about this? Yeah? So what is this? What is the language corresponding to this? Empty set. And what is the language corresponding to this? 0, right? So it's a concatenation of the empty set with something. What do you get? Empty set. Okay. What is this? What is this, by the way? 0, 1 star. So what is in 0, 1 star? Yeah, so what is the nice property of that? You know, so is 0, 0, 1 in that? Okay, so yeah, so it's a set of all strings with, it's 0, 1, 0, 1, 0, 1, 0, 1, right? Any number of 0, 1s alternating, right? Okay, then but it can be preceded with what? 1 or okay, and it's okay. So what is this? I mean, it's kind of hard to, we kind of see it, but what is another way of thinking about it? What does it not have? Is 0 on the front? No, yeah, 0 on the front it cannot have, right? It can have 0 on the front, right? Yeah, right? Can it have 0, 0? No. Can it have 1, 1? Is everything else in that? Or no? Is there a string? So what are the set of all strings with no consecutive zeros or no consecutive ones? What do they look like? If I prohibit consecutive zeros and prohibit consecutive ones, what do you get? Yeah, this is what you get. Okay? All right? So alternating zeros and ones is one way of talking about it. Another way of saying it is that I'm prohibiting what? Consecutive zeros and consecutive ones. Yeah. Did I make a mistake? What did I? No, it's epsilon plus 1, no? Yeah? See, remember, what does epsilon plus 1 mean? That language has epsilon and 1 in it. So I don't have to take the 1 in it. Right? Oh, yeah. We'll come to it. Yes. Yeah, so his question is there any language which is not regular? Right? We'll come to it. In fact, this is a very simple class. It's not obvious. Okay. What is this? What is this? What is this? What is this prohibiting, or what does this look like? Think about it for a bit. I know, not try to answer it. Spend a minute. So, I will not repeat it too many times, but staring at the screen is hard to. You have to look at your paper, because the brain is not so good, no. You have to write. Really, I mean, if you can't do math if you don't write. I'm sorry. So you have to stare at your thing and scribble. Okay, it's important. In the interest of time, I would like to move for enough time. If people figure it out, still want to think, yeah. We have somebody clamoring to answer, yeah. Yeah, no consecutive zeros. Okay, any number of ones is allowed, but you can't have two zeros. Right? It's kind of related to this one, but we're allowing ones, any number of ones, right? But if you get a zero, you immediately get a one. Yeah. So you could okay. So one thing you have to be careful about, which is true of when we say two languages are the same, usually we realize that okay, one language is a subset of the other language, right? That means that we know that strings without two consecutive zeros, every string without two consecutive zeros is in here, but you also have to convince yourself the other direction, that this doesn't have any strings without consecutive zeros. That whenever you make a correspondence between two languages, one should be a subset of the other and the other should be a subset of this one, right? That's the only way we kind of convince ourselves that we are on the right track. Usually we make a mistake in one direction because we are not paying attention to it, right? So when we ask you to prove L1 is equal to L2, what does it mean? You have to prove L1 is a subset of L2 and L2 is a subset of L1. There is no shortcut, okay? There are very few problems where you can easily understand L1 is equal to L2, other than it is just a definition, okay? You have to mentally think, why is L1 subset of L2? Why is L2 subset of L1? Okay? So otherwise you'll make mistakes. Okay. Now I'm going to do the other way, right? We so far try to understand what those mean, but now let's design. That is, I'll give you a language and you tell me a regular expression for it. Okay? So that's actually the design problem. So bit strings with the pattern, bit strings are just 0, 1 strings, right? I'll just use bit string to say the alphabet is 0, 1. Either 0, 0, 1 or 1, 0, 0 as a substring. Okay? So I want a regular expression for all strings which have either, not either this or that, not either, right? This or that. Okay. So if you just said, tell me all the strings which have 0, 0, 1, what would you do? We already saw that, right? If you want a substring, what do? You put any string followed by this substring followed by any string, right? But I have or, so I want this or that. So this is just the union operation, no? So I want the set of all these strings and the set of all those strings. Throw them all together, right? That's really what we want, right? Yeah? And union is easy in regular languages. So this one solution is design principle. Whenever you say or, you can put union, right? Which is plus. Well, this is concatenation, right? 0 plus 1 star, 0, 0, 1, 0 plus 1 star is this all strings which contain 0, 0, 1 as a substring. And this is all strings which contain 1, 0, 0 as a substring. There are some strings which contain both, right? But that's okay because we're taking the union. Yeah? Is that okay? Okay. All right. Bit strings with an even number of ones. We kind of saw it too, but this is a design thing. What does it mean, even number of ones? How many ones should be there? 0, 2, 4, right? We already saw bit string, we saw in the other part, the strings with the number of ones divisible by 3, right? It's even harder than this, right? Not harder, it's related to this, right? So you kind of saw it already. So you just have to remember it or recapture that. Okay? All right. Okay. It's similar to what we saw, right? It's 0 star, and these are exactly the strings with exactly 2 ones, right? 0 star 1, 0 star 1, 0 star. Remember we had 3 ones, and now we have 2 ones, and then we take the star. Yeah? Because a string which contains just zeros, is this in this? Sorry? Yeah? No, right? So you have to treat this as a special case. Okay? I mean, this is not the only way to write it. I'm sure there are other ways of writing it. Just you have to be careful. See, this is why it's important to make sure that you see that it's the right language. It's not always clear. Okay, bit string with odd number of ones. Yeah. Yeah. So just to repeat, it's a natural thing to wonder. Do we need this? I claim we need this because this set doesn't have strings which are like 5 zeros. It is not there in that, right? Why is it in there? Because I'm forcing ones to be there. What does a star do? It only lets you get epsilon. It won't, I mean, you can't omit, right? It's a little bit, yeah, you need to spend some time. Okay, bit string with odd number of ones. So I want us to think like subroutines, right? Look, I already know how to get even number of ones. Can I reuse it? I don't even know what it is, but I have a regular expression for odd number of ones. So I should just be able to use it for even number of ones. I should be able to use it for odd number of ones. Yeah? How will you do that? Sorry? Yeah, so I have a set of all strings which are here, okay? So one way of doing that is this way, right? Let's look at where the first one is, okay? How does it, the first one, well, it'll have some number of zeros, then a 1, and then what should be the rest of the string? Have even number of ones, right? So I'll just call this R and I'll just put it this. I don't know what R is, but if somebody gave me R, I can just use this, right? Yeah? So it's like a subroutine, okay. Okay, the last two are hard, okay. That means, you have to, this last one is really hard, okay. And why is that hard? I mean, I'm not going to do it in lecture. Bit strings that do not contain 0, 1, 1 as a substring. Okay, this is hard. Why is it hard? Because we are saying not something, and the operations of regular languages are not very natural to do complementation. Okay? So suppose we knew that, complementation was allowed, then this would be easy, right? Because we already have a regular expression for strings that contain 0, 1, 1 as a substring, right? So we say, let's take the complement, right? But that's not allowed in regular language, right? It's not closed under this operation. So this is a bit hard. So how do you design this? You have to think, okay, what are all strings which don't contain 0, 1, 1? And figure out what they look like and see if we can put that as a union of things that are easier, okay? Okay? So I don't want to tell you the solution right now. I want to think about it. And I wanted to illustrate the point that it's hard based on the definition of regular languages to do complementation. Okay? The same thing with, here is the thing, bit string with an odd number of ones, right? That was easy for us, right? Okay? And an odd number of zeros, okay? Why is this also hard? Because it's and, right? What does and mean? It's intersection, right? So this we know how to do, right? Odd number of ones, we already did it. Odd number of zeros is the same as flipping zeros and ones, right? It's the same thing. But I want both of them, right? What does that mean? I only want strings which satisfy both properties. So L1 intersection L2 is what I want, right? But I can't do it in regular languages naturally, okay? So that's why this is hard, but you can do it. These are actually regular languages, but it's not obvious that intersection of two regular languages is regular because we didn't define it that way. It's not obvious that the complement of regular languages is regular, right? But they are actually, and we'll see why. Okay, so I'll skip this because sorry, coming back to your question. So the natural thing is, oh wait a second, maybe every language is regular, no? Second, oh, wait a second, why, then it's not interesting, right? If every language is regular, it's not interesting. At some level, it's not interesting. So is there any language that is not regular? Okay, here is a simple language. What is this language? It is some number of zeros followed by some number of ones, where the number of zeros is equal to the number of ones. This is not regular. This seems like a very simple language, no? Yeah? It's easy to write a program if I give you a string and say for this language, right? If I ask you to write a C program to check whether a string is of this form, can you write a C program? Yeah? Easy, right? Okay. So, but it's not regular. Okay? So, how do we prove it? Do you know how to prove it? It's not obvious how to prove it, right? Okay? Well, that's one thing we'll try to prove. So, this is another question, right? If R1 is regular and R2 is regular, is R1 intersection R2 regular? If that was, then we can easily check that the previous things, right? Bit strings with odd number of ones and odd number of zeros would be regular, because one is regular, the other is also regular, and so this would be. It's not obvious from the definition, it is true. And again, same thing with complement, right? So it's not obvious, and this is why we need to think of regular languages. We define it in one way, and later what we'll do next lecture is that we are going to define it using we'll define a different model using machines called deterministic finite automata, and we are going to later prove that the deterministic finite automata and regular languages are the same. Okay, but that will give us some power in arguing about some things are easier with that definition, some things are easier with this definition, and that's how we'll do it.